Okay. All right. Yeah. Go ahead. Guys.
Okay. Hi, everyone. So today we'll be talking about Caesar, mitigating conflict-based cache attacks via encrypted address and remapping. I know that was a lot, but hopefully we break it down for you in this presentation and make it easy for you to understand.
First, we want to start with going over cache importance. So the whole point of cache is that we want the fastest access to data as possible. And the idea is that cache is very low latency memory. And the larger your memory gets, the slower it becomes to actually access the data. And one of the things that you should note is that the fastest cache is very expensive. And this is the cache hierarchy that we usually see. And why I'm talking about cache so much is that nearly all modern systems use cache, and our attack that we will be specifically talking about and learning about will be based on cache.
So now we can talk about the problem. So the cache eviction attack. So the problem is going to be this cache eviction attack. And so if you look at the diagram on the top right, you'll notice that for each core, there's some things that are private to the core, and there's something that is shared between the entire CPU. So if you look at the registers, the L1 cache, the L2 cache, you see that that's private to the core, but you'll notice that the last level cache, the L3 cache, is shared between both cores. And of course, the memory is shared between all the cores and all the CPUs as well. And so while we notice that L1 and L2 are private, how do we protect memory? We already answered this in an earlier lecture where we talked about virtual memory and using page tables to make sure that processes can't read or write beyond where they're allowed to. But the thing is, you'll notice that this last level cache is still shared. So that means that there is a potential vulnerability there. And so the reason why we share it in the first place is because it allows us to have effective space utilization. So let's say you have 3 cores, you have core 1, core 2, and core 3. Core 2 and core 3, they're not using a lot of memory. And so therefore they're not using a lot of cache. And so it makes sense that core 1 gets access to most of this last level cache. And that would mean that the space utilization is effective. But the issue is, since this cache is shared between all the cores, this opens up a side channel to this cache eviction attack. And so now I'll talk about how this cache eviction attack occurs. So if you look at the diagram on the bottom right, so what the attacker does, so the idea is that there's an attacker process and there's a victim process. And so the attacker process will first figure out where the victim is modifying in the cache, in the actual cache. So they'll find the cache line. And then within the cache line, they'll find a cache set. And then this will be called the eviction set. So once they find the eviction set, they'll load the eviction set with their own values. So if I'm the attacker, I can just set it all to 0, for example. And then over time, I'll see how the victim will modify the cache. So I can repeatedly check for cache hits and cache misses. So the victim were to load their own values, let's say, then I'm going to see a cache miss because my own value will not be in the cache anymore. And so if I want to pull that back in from main memory, that's going to be a cache miss, whereas otherwise it would be a cache hit. And so we do this, we analyze cache usage over time, and finally we profit, which is to extract valuable info from the cache.
If you're wondering what the question marks are for, we usually don't know what the attacker is actually doing in the analysis step. So the idea is that let's not let the attacker get the information in the first place so they can't analyze it. So that's why it was there.
And then so the impact of this attack and potential solutions. So hundreds of millions of processors are affected by this attack. Pretty much any processor that has this last level cache that's shared between cores and has multiple cores is affected by it. And the attack is actually pretty devastating. So an attacker can use this method to infer and extract AES keys. So this attack is both widespread and it's dangerous. And so we really want to find a good solution to this problem. And so one solution is this preservation-based method, which is basically you have this last level cache, which is shared between each of the cores. Well, why don't we just make that private to each of the cores, like we did with the L1 and L2 cache? And so, of course, there's an inefficient use of space, but that pretty much solves the problem. And so moving on to the threat model, as we discussed earlier for the cache eviction attack. So we're assuming that the attacker has their own hostile process that's running on the computer. And there's also a victim process that's running on the computer. And that victim process will modify the cache over time. And so we're assuming a very conservative or pretty much ideal attack scenario. So one is that the attacker can identify where the victim is modifying it. So they can identify the eviction set of the cache. And the second thing is they can form the eviction sets quickly. So if it took them a long time, let's say it took them like seconds, then it's possible the victim could be doing a lot of actions within that time that it takes for that attacker to check and see what changed. And then finally, there's the assumption that only one other application is modifying the same eviction set at the time. So that means that in a real world scenario, we could have, say, hundreds of processes running at the same time, and you could have multiple processes sharing the same cache line. And so in this case, we're assuming that there's only one attacker process, one victim process. So overall, this is a very ideal attack scenario.
Let's go over the main contributions of this paper we're going through. And one of the things that people will usually ask is that you probably will think, why can't we just randomize like each cache location? And there is an issue with that. So we have this randomizing overhead, and if you basically use the cache and as like random, like we put things randomly, so that would make it harder for an attacker to try to gain more knowledge about what you're doing. You need a very large table to keep track of where everything is. And even if you have like operating system support, you'd be wasting essentially with this table about 1.25 megabytes for a 8 megabyte like last level cache, usually L3 cache. And that's pretty huge. And like I said, cache is pretty expensive and we don't have very much of it. So we don't want to use that much of the cache for that. And again, like I said this is assuming operating system support. The problem with that is that operating system support requires the operating system to basically know, oh, this is basically like a trusted and this is a non-trusted application. And with that, that's a problem because you need to actually figure that out. And trusted applications can access the mapping table, and unprotected, which are like not really trusted, cannot. So that's the idea. But can we do better? No. Okay. Thank you for the press. Okay.
Yeah.
Thank you for. Okay, that's a joke. It's a joke. Just to wake people up. I know it's the first presentation of the day, so let's just keep going. Okay, the main contribution. Okay. So the main contribution is used only in the last level cache, the L3 cache, and we are basically just using a cipher, like as the first step, on the cache addresses in the L3 cache, which is like the last level cache, and like I said, you'll be making the PLA to ELA, which is from the physical line, which we usually use physical line address, and we use an encrypted line address instead. And we're only using this for the L3 line or like the last level cache, I should say, because otherwise we'll be slowing down all the levels of the memory hierarchy. But we only want to want to have the performance cost in this specific attackable level. So we want high performance, and the papers show that we can have this with only costing 2 CPU cycles. This is not actually very bad because if you know what the last level caches usually are in modern CPUs can be anywhere in the hundreds of CPU cycles for getting information. So 2 CPU cycles isn't too significant. And the overhead is of about 10 bytes for the encryption key. So it doesn't seem all that bad in terms of the performance cost. And to continue, what the paper actually talked about was season, which is going even further with this. And we have an encrypted address space. So in this cache, in the L3 cache. And we are using the low latency block cipher that we just talked about on the previous slide. And but we want to improve this because you can still, as an attacker, you can still start to see patterns in how the cache is being used. If you don't have some kind of randomized, so you want to add some randomized component to this system to make it more secure. And the improvement is that you keep changing the keys to the LLDC, which is a low latency block cipher. And over time, you're gradually changing where things are mapped in the cache. Now, of course, you will think, oh, there is a cost for that because remapping does take some performance, right? That is some things you have to do. But as they showed in the paper, there's only a 1.1% performance slowdown on average. And there's only 24 bytes of space cost, which is, on the cache of an L3 size, which is usually the megabytes of size, that's not bad at all. And the benefits are that it tolerates 100 plus years of attack. And there's no operating system or software support needed, which is honestly makes this a lot easier for someone to implement. Now let's go to the experimentation and evaluation parts.
So experimental methodology, let's talk about both CEASE and CESR. So the way they tested this was they ran different workloads on these circuits. So they picked 29 workloads from the spec 2006 benchmark and 5 workloads from this gap benchmark. And so these are established benchmarks, and you can find the workloads for each of them. And so if you look at the diagram at the bottom, you actually see the average or the performance for each of these workloads and see how well it did with this new circuit and without it. And you can also see that there are, so they also made 100 more mixes created by mixing each of these 34 benchmarks. And through this, they were able to see like what the average performance would be for an average workload. And not only did they do this, but they also sampled 1 billion instructions. So we can be sure that they tested this thoroughly, and it wasn't just a lucky set of 100 or 1,000 instructions. And so with 1 billion, we know that that this performance is what we expect.
Okay, so let's go over the security benefits first before we talk about the actual performance costs. So Caesar, which is what we're going over in this presentation, is very secure. Like I said, it was over 100 years of attack, which is considered strong resistance to attack. And C's, which is without the randomization, which I was saying like remapping where things are in cache, it's still pretty secure, but but Caesar is still better. So like I was saying, C's is different because you don't remap, and like you can use these patterns to figure out where things are in the cache. And Caesar, this remapping can be used to make it even harder to figure out what things are happening in the cache. So as you can see, we have like a nice table that kind of shows in the paper what they found for how long it takes to for attacks to succeed. And you can see that there's pretty big difference between Caesar and no C's and no Caesar, like just C's, just Caesar.
So while we talked about security benefits, we can talk about the overall performance. So C's is a bit faster, but it has less security benefits, as we saw in the previous slide. For the fastest workloads, the speed difference is about the same. So if you look at the diagram at the bottom, on the right half, you can see that both C's and Caesar, they're almost at the same performance. Whereas for some workloads, yeah, they can be a bit slower, but on average, we see a 1 to 1.5% slowdown. And so there's 3 main sources of overhead. One is the encryption latency, one is from the cache remapping interval, and the third one is from the miss rate. And so I'm going to go through each metric right now and how it affects performance. And so talking about performance by metric, we can start first with the cache latency. So the cache latency results from encryption and decryption taking a few more cycles. So we can see that if it took 1 cycle, there's a 0.5% slowdown. And if it took 4 cycles, there's a 1.75% slowdown. But the thing is, we can actually reduce this with even lower latency block ciphers. So in the paper, they mentioned that they could use either like better hardware to have this be a bit faster, or they could use a different implementation, which is less secure, but would result in lower cycle time. And the second thing is remapping frequency. So the whole idea with Caesar is that every 25, 50, or 100 accesses, we actually remap the cache. So we basically randomize it for every n accesses. And so if you look at the diagram on the bottom right, then we would think that this remapping should result in a significant delay, but it actually doesn't. So even between remapping every 25 intervals and between remapping every 100 intervals, the difference is only 0.1%. So it goes from a 1.1% slowdown to 1.2% slowdown average. So the results are really remarkable for this level of safety.
Yeah, you can see that in this graph, this table.
Yeah. And then the last metric, which is miss rate. So because we're remapping and we're encrypting this cache, there should be an increase in miss rate because it's not like the things are in the same place every time. And so this remapping should also result in a few cycle delay as well as increasing the miss rate. But the thing is, if you look at the giant table on the right, where they compared all of these benchmarks between C's and Caesar, the miss rate barely goes up. And so we only see less than 8% slowdown across all of these benchmarks, which is really remarkable. And then the final thing, so any other performance metrics or any other overhead. So as far as logic is concerned, it's slightly more complex because we're using 2 more low-level block cipher circuits. So it adds a little bit more in terms of transistors and more to the design. But in terms of the actual CPU, that's fairly minor. And then as far as energy and power is concerned, there's a 0.1% or 0.2% power increase and a 1% energy increase, which is negligible overall for the security benefits.
So just some discussion points to think about is that, like where else can you use Caesar, in other than the cache? And because this is a pretty secure design, so like where else would it actually be possible to use? And is there a way to make a software-based implementation of this? And what are the drawbacks and benefits? Some things that you might think of off the top of your head is that it will likely be slower to the software, but you have the it's much easier to change whatever you're using. For example, you could change the way you're doing the low-level block cipher a lot more effectively if you had it in software. And can we extend this attack and this resistant method to different architectures and different cache layouts? So what if you didn't have a shared cache, but somehow a cache was actually able to be attacked by something else by using some other type chain? Would this also be used in that case? So it's just some things to think about.
Thank you, guys. Any
Thank you.
questions?
Any questions? Yeah, this is by the way, there is a follow-up paper to this that shows that this is not effective.
Oh, wow.
Yeah, so technically an attacker can kind of like, fill the cache entirely and use that in order to, can you go to that slides that you actually describe how the key works to second contribution, basically? I can maybe describe it. Yeah. So the way this works, guys, is remember for cache side channel, you need to create what's called an eviction set, right? So you need to find a set where you have a bunch of different addresses, and all of them are mapping to the same set. And once you find that, that set has to be the same set that the victim also accessing, okay? And this basically this paper, the solution is kind of trying to randomize the addresses. So it would be very, very difficult for the attacker to find that eviction set. The way this works is that what you get normally is you have your addresses, you do the address translation, you get the physical address, and then you directly access your last level cache or LLC, or generally your cache, right? So what these guys suggesting is that, this address is PLA, your physical address. Let's map it to another address called ELA, or whatever you want to call it, basically the encrypted address, and then use this to access your cache. In order to do that, basically some sort of an encryption. It's not really an encryption. It's more of, think about it as more of a mapping. So it's like a pseudo random function in some sense. And they use this key to do this mapping. And this way, in order to find, given that this from here to here is like a random mapping, in order to find the addresses, the attacker basically needs to scan the whole cache. And they show that this is actually, the chances of finding multiple addresses in the same set is very hard. It's actually it has a very nice proof for that as well. If you're interested into it, go and look at it. It's basically what's called a birthday paradox. So probably how many of you have heard about birthday paradox? Yeah, so the birthday paradox is that, the chances that you and someone else in the class have the exact same birthday is not that much actually. So you think that, there's 365 days per year. So you need probably, a lot of people so that the chances that you have one person, more than 50% that, some person and you have the same birthday. But in fact, it's actually only 23 or something like that. So if the class size is more than 23, the chances that there are actually two people that have the same birthdays. And that's what's usually called big balls and buckets or generating the birthday patterns. There's a nice proof for that as well. So this is actually based off that and saying that, it's the chances of finding multiple addresses in the same set is very, very low. And then the nice thing is that, the overhead though is that, whenever you want to access your last level cache, you need a decryption as well, right? In normal scenario, what you would have got is you have the physical address, you go to the cache, you bring the data, right? But this is basically in your critical path as well, because every time you need to access and bring something from your cache, you need to also go and decrypt that value. And but the only thing is, the rest of the paper was mainly showing that, oh, if you have this only 2 cycles, this much overhead, 4 cycles, this much overhead, and so on and so forth. Another nice thing that they did is that remapping things that basically, some part of the cache was used at old key and some part of the cache used a new key in order to be encrypted, decrypted, and then they used this additional bits to know which one was old and which one was new. And that way they significantly improve their security as well. But generally, going back to my original statement, people have shown that there's a follow-up paper to this that show that it's actually finding these evictions is not as difficult as we were thinking, because the attacker can basically start scanning through the whole cache, and that's not too difficult to do. So they can fill the whole cache, and this way they can actually get the evictions that they want. So the assumption here is that, if this is large enough, then it's secure, but in reality, cache is not that large. So the attacker basically can kind of like brute force through the whole cache. Okay? Any questions? But again, the whole story about cache sections is still an evolving thing. So there are, again, attacks and defense going on and on. But these are one of the very useful, ways of trying to protect, although it's not exactly working.
I see.
All right. Thank you guys.
Thank you.
Yeah,
It's
you
like-
can take your laptop.
Oh, yeah.
Oh, yeah.
It's like the whack-a-mole essentially.
Yeah,
You fix
exactly.
one thing and then
Then we should probably
someone.
end the call.
Yeah, and then
Leave the call.
just stop sharing and leave the Zoom. Yeah. Who's next?
This is my secret.
Okay.
It's always something.
You want to use your own laptop or? Okay.
So,
Yeah. It's A1. The meeting ID is.
it's like,
A1.
one,
01
0,
88 295 another 5.
Yeah.
You're in? Okay.
Should I share my screen for the
Yes, please.
presentation? Do I unmute or no?
So just mute yourself, and also make sure your speaker is also off.
Speaker is off.
All right. Boom slideshow. Can go.
Good morning, everyone. Today we're going to present the paper FPGA-based remote power side channel attacks. My name is True.
And I'm Adam.
All right, so first look at the power context. So right now we are seeing problems of hardware acceleration in both cloud and mobile computing. So usually we want to accelerate the training of machine learning models. And field programmable gate arrays, FPGAs, are usually the top choice because they provide flexible and reconfigurable acceleration. And now users have fine-grained control over FPGA hardware provided by service providers. And in most cases, several users will share one single FPGA board. And we know that shared resources often have vulnerabilities. So how to exploit the vulnerabilities? And can we initiate a remote power side channel attack? But wait, don't power side channel attacks require some physical proximity? So conventionally speaking, yes. So usually power side channel attacks require an oscilloscope or some equivalents like a voltmeter to measure power consumption. And there is long-standing assumption in the academia that remote physically secure systems are immune to parasite channel attacks. And it's usually the case of a remote data center, which are utilizing FPGA boards. But in this paper, we are going to see how we can initiate a remote parasite channel attack just using the FPGA. And before we get into that, we need a little bit background about the FPGA. So an FPGA is a flexible integrated circuit, and so the logic blocks are the main building blocks of an FPGA board, and they are programmable via hardware description languages like Verilog, if you have taken CS M152A. And there are multiple applications of FPGA. So for example, the hardware acceleration and also hardware prototyping. And that's why most tech companies have started to provide FPGA services. So for example, Microsoft has its Project Catapult, and Amazon also has its EC2. And they all share the same idea of virtualizing and sharing resources. So that's pretty much like what the operating system is doing. And so that a malicious user can try to do something bad or try to write some malicious circuits to steal information from others. And another important step is the ring oscillator circuit. So basically the one on the left is the ring oscillator, and the ring card is a counter. So basically a ring oscillator has two inputs, one is enable and one is feeding back from the output. So when the enable is high, the output will kind of oscillate between 1, 0, and the time between every two digits is actually depends on the propagation delays of two gates. And also the propagation delay actually depends on the input voltage, and that is the characteristic of MOSFET. All right, so the strike model here is that actually in this paper, we're going to see two attack scenarios. So the first one is an FPGA to FPGA attack, and the second one is an FPGA to CPU attack. So in the first one, we assume that we know the circuits of the victim logic. So for example, it's an RSA crypto module. And in the second scenario, we assume that we know what's running on the victim core. So for example, we know that it's running a RSA decryption program. And we will utilize our FPGA malicious circuits, try to steal information from them, sort of building a side channel. And yes, so, and we also assume that we don't have any direct or physical access to the victim. And there are some kind of isolation mechanism, and still we are trying to build the side channel. And our goal here is to steal confidential information from the victim, such as private keys in an RSA crypto module. So basically, it's the confidentiality in the SAI triad. All right, let's do it.
Okay, so the main contribution to this paper is that they took the ring oscillator circuit that we described earlier, and they managed to turn that into a way of power monitoring the FPGA and also anything linked to the FPGA's power supply. So we look back at the ring oscillator. The actual ring oscillator used for the system is just a very simple one. It only has one inverter stage, and in the counter on the right, it will how about you calculate its frequency if you specify some constants, a reference clock, and I think a few other parameters. But you can see equation 3 down there will let you calculate the frequency of that particular ring oscillator from its parameters. But the issue is that one ring oscillator by itself is located somewhere on the board, and its results may be subject to it might be affected by where exactly it's placed on the board, and also just random noise and things like that. So what the authors did is that you can see in the picture over here, that's like the available FPGA fabric for their design. And they put 20 such ring oscillators here. And this way, they're all spread out around the available FPGA area, that kind of averages out any spatial dependence that they might have in terms of the voltage and the frequency. And now that you have 20, you can just add up all the results, and equation 2 there kind of links in with what Shor was saying. There's you from the design perspective, you know roughly what frequency the ring oscillator is supposed to be operating at. And any deviations from that, once you aggregate them together, it's most likely linearly scaling with the voltage in the area. So now you can obtain a good picture of the FPGA power consumption. And after this, you just have a side channel for voltage and power monitoring, and you can proceed to attack it as you normally would with other side channel attacks. So the evaluation methodology for this paper, the authors did a lot of testing. The first thing they wanted to verify is that, wait, does this actually work as we expect it to? So their goal, they created a bunch of power viruses, which are simple logic circuits that when you activate them, you know how much power that they'll consume. And they just tested that to make sure it works. They also actually, I should mention, they tested everything on this particular development board here. So this is a Zinc 7020, which is made by Xilinx. It's a system on chip that has an FPGA, and it also has a dual core CPU that runs on the same power supply. So on the actual attack testing, we mentioned the two attack scenarios from earlier. There's you have an FPGA, you have an attacker program, and you have a victim program on the same chip. You want to see if you can get information from the victim program, you can get isolated. And the objective here is the victim program is a RSA decryption accelerator. So we discussed RSA in this class. It's a asymmetric encryption algorithm, and the decryption part is where you need a private key. And that's something that presumably you want to keep private. And the reason why this is vulnerable to side channel attacks is that in the pseudocode over here, there's an if statement for the modulus of the key. And if the key bit is 1, then it will be running a multiply circuit and it will be running a squaring circuit. But if the key, if that particular bit is 0, then it will only be running the squaring circuit. So there's a differential behavior depending on what the value of the key is at a certain bit. And you can use this for timing attacks or power analysis attacks. And the other test is the FPGA CPU power analysis attack. And this one is pretty similar, except the CPU's architecture is a little different. So they wanted to make sure that the monitoring system on the shared power supply still works accurately. And the CPU also has, in this case, has defenses against timing attacks. So really power analysis is the only avenue. So, okay, does the power monitor work? And the answer is it actually works very well. So you can see on the graph on the lower left, the power virus instances is just how much power we expect for the test program to consume. And you can see there's a very strong linear relationship between the power consumption and also the frequency. So the frequency of the ring oscillators goes down linearly as you get more power virus instances. And on the graph on the lower right, that's a chart of if spatial dependence is a big deal. So they had 20 ring oscillators and arranged on different parts of the board. Over here, row 5 is the one that's closest to the target program on the chip, and number 1 is the furthest away. You can see that there's the one on the further away you go, the smaller the differences it picks up, but they're still pretty significant, so it's not a big deal. Another fact that they found is that there is a question of how often should you sample the ring oscillators, or like what time period do you want to wait before you measure and aggregate the results. There was a little complications with that, but they said typically it's not a huge deal. It's just that if you want to measure a very small voltage deviation, then you need a bigger sampling period. But for the purposes of the attacks, it's not an issue. And for the FPGA to FPGA, so it actually worked very well. So you can see on the plot on the lower left, that's an RSA power trace. And you can see clearly the power trace looks different depending on what the bit of the exponent is, and this will let you recover the key. It's not exactly perfect. So on the table 1, you can see some results here. There are 3 kind of super columns: PR, ISO, and no PR. PR means controlled place and route, which means on the software lets you put the ring oscillators or whatever exactly where you want them. Isolation means that there's like a wall of unused logic gates that prevents you from like putting logic right next to the victim logic. And no constraints means that you don't actually have a choice of where to put it. The software just picks it depending on what it thinks is optimal. So within these columns here, you can see there's errors, and those are the average number of errors for each bit of the RSA decryption key. And so you can see that it's not perfect. It gets higher with the more constraints you have on the placement, but you can get around this by just replicating monitoring system and just do a majority vote. So statistically, it'll just average it out. So for example, if you have traces in root, you only need 3 to 5 traces in order to perfectly reconstruct the key. It's very simple from an attacker's perspective.
And then in the second scenario, which is an FPGA to CPU attack. So basically, the authors are using an FPGA system on chip, which means that a dual core CPU and the FPGA fabric are actually embedded on the same silicon die. And usually they share one single voltage regulator so that the FPGA can still read some voltage information from the victim core. And this also happened to be the case with the dead board that they are using. And they want to test, so first they want to test if the FPGA can actually listen to the CPU activity on the victim core. And from the figure here, we can see that actually from the sample 23,000 to 59,000, there is kind of a drop in the frequency, which means that the CPU is up from in that time period. And this is because they are running a 8,000 character string comparison on the victim core. And also, this means that the attacker is able to measure CPU activities from FPGA. And we can also see that some timing information is also leaked through the power side channel. For example, the setup of the program and also the program's actual execution time. And usually, there is also another side channel, which is the timing side channel. So the idea here is that because the program might have different branch, and when the so for example, if the digit is 1, then the execution time is actually 460 microseconds because there is some of flushing and branching stuff, and that would cost extra time. And if D is just 0, then the execution time would be smaller because we don't need to worry about the branching stuff. And one mitigation technique is trying to delay both cases to the worst case so that the attacker won't know if the current digit is 1 or 0, and this one is and this technique is implemented in the victim core. However, through our power side channel attack, we can still recover the private key, and we can see on the we can see in the figure on the right, we can still recover the key to be 0 for the actually the lower 16 bits and 1 for the upper 16 bits because the time actually goes this way.
All right, so the authors mentioned some or hinted at some discussions of future work that we could do on this topic. So the first one is the ring oscillator based power monitor is not the only kind of power monitor you can make on FPGA. There's others you can do with, I think, you just have a long train of gates and you can track the delay from one to another that can monitor the voltage too. This particular one is fairly simple. It has some zone strengths, but the one disadvantage is that if you're getting all your information from frequency, that there's a limited resolution aspect to it. So in this RSA attack, then the resolution is perfectly fine. But we want to know is when is your target so sophisticated that you need a precision that the ring oscillator can provide? So that's something they could look into in the future. And another area that we can research is how can we detect power monitors or other malicious FPGA code if you're trying to upload it to someone's web servers. We're familiar that with standard programs that you run on your laptop or a server or whatever, that you can scan code for anything that looks suspicious. But for FPGAs, it's a bit more difficult because you're specifying a physical layout of gates. Those are not always easily interpretable as instructions. So how do we do this in a way that is not going to take forever is an interesting question. And some thoughts that we had when after we read, I guess, the paper is the countermeasures for here. Besides, we mentioned you can scan FPGA code ahead of time. Is there also something that we can do for the power side channel intrinsically? Because this attack hinges on the fact that even if we isolate the logic of different parts of the FPGA, or even if the FPGA and the CPU are two completely different parts, as long as they share a similar power supply or a voltage regulator, then that side channel still exists because that is actually fundamentally the shared resource that's going up. But is there a way that you can isolate the power supplies from like the fluctuation in one section from another? It's probably not easy, but it's something worth thinking about if you need a really secure device. And another interesting factor is that the temperature is another factor of the frequency of a ring oscillator. So in this paper, they only want to look at voltage for understandable reasons. So they just try to minimize the effects of temperature as much as possible. But temperature itself, you could think about it as a side channel. I imagine maybe it's not as good as voltage, but it's worth thinking about.
And also, if we were to remove all the ring oscillators in the FPGA, but there are actually some positive use cases of ring oscillators. So for example, we can try to detect DOS or DDoS attack. And also, because Intel has bought Altera and also AMD has bought Linux, they are trying to sort of have FPGA embedded in their own system on chip so that they can do more stuff. So Intel Xeon has FPGA fabric modules, and we are wondering if it's possible to break the SGX enclaves provided by Intel through this power side channel attack. And also there are multiple IoT devices and multiple devices connect to the FPGA to accelerate their program. Is it able to hack into them through this side channel? And that basically concludes our presentation. Thank you.
Hope you enjoyed the cat pictures.
Any questions?
Thank you so much. Any question, guys? Yeah, this is kind of like a new kind of trend model these days. We're also getting that you have a cloud computer, and then you have a bunch of all these other additional components such as an FPGA, because FPGA could be useful for many different situations. And a remote user can also access that FPGA. And what these guys showing is, what you can do is that given that you can basically program your FPGA with whatever you want, you can maybe design a ring oscillator on that and then basically just monitor the power consumption of your CPU. So all the FPGA does is that instead of doing something useful, it's just basically a ring oscillator. In other words, it's a sensor for the power. And they showed that what you can do is that having a good sensor can reveal lots of secrets about the system. And not only the CPU, you can also maybe sniff activities of other FPGAs, maybe, and you like saying in your discussion points, maybe you can use it for IoT devices or other things, right? So basically, as again, going back to the conversation that we had, convenience is one thing that we definitely want, right? So what you want as a user is being able to not only access the CPU, maybe it would be nice to have an FPGA on the side to maybe implement some useful things and so on, right? But on the other hand, it means that it opens the door for new types of attacks where the adversary now can, program your FPGA and can do lots of other things. So it's an interesting, very interesting observation, actually, very creative way of thinking about how to use the FPGAs. Thank you, guys. All right, let's have a quick break and then we can resume at 11. Any question about anything else before we continue? About the project? Is everybody clear? Yeah, you can set it up.
How much longer would you say this one is compared to the last one?
I don't think this should, I think it should be the same or even less. It really depends on whether you have used, machine learning pipelines before. If you have, then it should be very, very simple.
Yeah.
If you haven't, then you need to spend a little bit of time to get yourself familiar with like Jupyter Notebook and the syntax and things like that. But it's not, I mean, generally the amount of code that you have to write is not that much. 81 01 88 29 55. Without video, mute yourself, also mute your speaker.
That works. Means I go back a slide.
Yeah.
Some over review.
Yeah.
Okay, sure. All right, so we're looking at wireless charging power side channel attacks. I'm Elijah Ellsbury.
I'm Helena.
Let's get into it. So the sort of overarching problem that this paper is looking at is through performing inference attacks by monitoring the power draw curves through wireless chargers. This was prior to, according to this paper, it hadn't been done before, it hadn't been proven. So this has the possibilities that we can extract data, extract different information from those power draw curves. As you can see on the right side here of this figure, different websites that the device is loading, the smartphone that's sitting on the wireless charger, it has a different sort of current pattern, so we can build a model that infers what website is being loaded from those current traces. The threat model for this one requires that the adversary has the means to insert a circuit, a very simple circuit, as you'll see in a moment, that can monitor the current draw of the wireless charger. They don't need any sort of malicious software or otherwise access to the device. All they need is the compromised charging station with current monitor inserted in series. The diagram down here sort of shows that. We have the malicious current monitor that's feeding data into a classifier. Everything else works completely normally. So here's our experimental setup. This is used throughout all the paper. I believe they said it was around $30 in parts. It just required a simple, we have a current sensor and microcontroller here, just a DC current sensor. And this is where one of the big limitations of the paper comes from, because this was limited to sampling at 700 hertz. So it's sort of, sorry, other power side channel attacks involve more sophisticated equipment such as oscilloscopes. We don't have that luxury here. We only have 700 hertz that we can actually pull the current draw at. So that's a big point for this paper.
But then that's what makes it extra strong, because it's essentially proving to us what we can do with only 20 to 30 watts. So for some background, the wireless charging, so that's a GIF of capturing the cable. With wireless charging, that wouldn't happen. And how that works is it's just from the simple electromagnetic induction principles. We have the transmitter, which is a charger, supplying power to our phone, which is a receiver. But our phone is going to ask for a certain amount of power supply. And that depends actually on the battery level that our phone is on right now. We're going to talk about that in a bit. But basically, the phone is going to request the power from the transmitter. And the only conditions for this process to initiate is that both are Qi compatible. So Qi open interface is the most prevalent wireless charging protocol nowadays. It supports over 200 devices on the market right now. And as long as the devices are within range, which is something like 4 centimeters, this process is going to initiate without knowledge of the victim. They don't even plug in anything, which is why the attack model in this paper is actually pretty strong. And what we need to know is the battery charging cycle. So we all know, like, the battery, when we plug it in or not plug it in, it doesn't just always charge with the same current. The first phase here happens when we're at a relatively low battery level. That's called constant current charging. So basically, the charger is giving us as much current as it can until we reach like a certain voltage level, which is about 4.2 volts in this paper. And then we enter the second charging phase, which is constant voltage charging. With that phase, the current supply is going to drop. So then the V voltage can be controlled to stay at a maximum limit. And then finally, when we reach the perfect number, 100%, we cannot really supply current anymore because the battery is already full. Now, what the charger does is that when we lose a certain like slightly some battery, we're gonna compensate for that and provide some popping charge. So that kind of gives us an intuition of how the current traces can reveal certain fingerprints to leak our information, because when we're at full battery level, the current traces drawn from a charger is going to directly reflect the phone activity that's happening. And we're going to talk about the attack and evaluation methodology first here, because they're helpful for us to understand the main contributions. It's actually pretty straightforward. Basically, we just need to collect a bunch of different current traces on different devices and on different websites. So they did it with iPhone 11 and Google Pixel 4. They collected them separately, both with wired charging and wireless charging, also separately, so that they can compare to see if there's any parallel between wired and wireless. They chose the websites from Alexa top sites, and then this collection process is actually automated. So like they have something that can trigger the phone to load the website, and then a current monitor to monitor the current traces, and then it can actually align it so we don't have too much time shift happening with our traces, so it's easier for data analysis. And the classification algorithm, it's basically a 1D convolutional neural network. So we know CNN is most popular. Its most popular use is probably image recognition, but here we only have 1D. So we don't have like pixels. We don't have a 2D image. We only have a 1D data string. That's the time versus the amount of current drawn. So with that, we can break that whole trace into like a huge number of segments with a big overlap, and then we can use a sliding window to like slide through that. And each segment gets 1 vote. With that, we can use the majority vote algorithm to train the classifier. What's special about this is they have this long short-term memory layer, other than the 3 convolutional layers. And what that does is going to learn the order dependence, because our segments are related, they're overlapping, they're not like just scattered around and like, you know, so they can learn the order dependence from that and train our classifier to have the correct output.
All right, so now we'll get into the main contributions of this paper. So first off, the first major contribution, as we sort of saw in the intro, is the discovery that wireless chargers are prone to this wireless power side channel attack. So we see different websites here over multiple trials. Each website has the sort of current pattern that we mentioned before, but that current pattern is repeated over several trials, which proves that it's useful for training and testing models that can infer based on this data. So looking at, we've seen wired charger side channel power attacks before, and this paper shows that they are equivalent, shows that they both reveal the same amount of data rather, although the wireless data or wireless current traces do have more noise within them.
This is a heat map showing basically, again, the parallel between wired and wireless charger attacks. So they trained the classifier on wireless charging and then tested on the wired charger using that same classifier. And we can see that the diagonal basically means that there's more color there. That means it's kind of working well. Yeah, so this proves that it's interchangeable and there's big parallels. So basically the point here is that we can achieve with our wireless attack what we can achieve with wired attacks, which is a much more well-studied field.
So the third point here, the third main contribution of this paper is the importance of the battery state of charge. As we can see by a lot of these diagrams, we have different iPhone generations tested in both wired and wireless configurations. The iPhone 6s doesn't natively support wireless charging, so it was omitted here. As we can see, below a certain threshold for each phone, we're getting very little data. We're getting very little sort of pattern in the current trace. We're just getting a very, very linear line. or sorry, a very linear pattern. And so one of the considerations for these models is that the state of charge needs to be very high. In most cases, above 80% was where it started to become useful for classifying this data.
This is kind of like a summary on various criteria they talked about in the evaluation. So some we have already talked about. One of the main contributions is a battery state of charge. I put traffic lights where where the criteria is case dependent. So here, what it means is that if so this table shows if our classifier is resilient to each of these criteria. So for example, for trace duration, most of the data they used had like traces of about 10 seconds. But then they realized that if you shorten that duration a little bit to about like maybe 6 or 8 seconds, the accuracy does drop, but it still works pretty well. But if you keep shortening it until it reaches like a certain threshold of like maybe 2.5 seconds, the classifier won't really work because that's like the time the website takes to load. If we fall below that, we're not really going to catch much of the characteristics. Two things to know here is that it's not resilient to different device types or time between training and testing. So device types is the train classifier from an iPhone won't work on an Android phone. So that's like a big limitation here. We don't know whether in future we need to train the classifier for each device, or we need to somehow gain knowledge on what device we're trying to attack. And then for time between training and testing, it's like if we train a classifier right now, and then if we were to use that on an attack next year, it's not going to work at all because the content of the website or like media on the websites that we're looking at change massively over time. So this is time sensitive. Basically, what it implies is that we need to keep updating the training data. We need to keep training the classifier to keep up with the current attack conditions.
So what can we do about this? Well, we could panic. All our data is just done for. We set our phone down anywhere. There's a wireless charger embedded in it. Our data's gone. That's it. End of presentation. But actually, the paper doesn't go too into depth on a lot of these solutions, but it does make mention of them, and we explored some of the papers that they came from. So the first one is reshaping power signals. This was shown to be effective in other papers. We can also perform non-malicious injection of, as the paper quoted, meaningless code. What this does is, as it executes more meaningless code, the power curve will also change, making for a guess that's barely better than choosing a website off that previous Alexa list at random. We can also perform filtering or other signal transformations. This paper actually quoted another paper that used a 60 Hertz low pass filter to reduce the guesses made based on the power curves down to just above a random guess. So again, very effective using signal processing techniques. We can also modify the signal at the power cell level down at the transistor level to manipulate it and again, obfuscate away certain details. One interesting point that they made is that iPhones actually have a location feature that may be embedded within certain wireless charging stations. So in the future, Apple might be able to extend the sort of functionality of it to make public, away from home wireless charging stations be marked as untrusted and not charge above those thresholds where these attacks are effective. Finally, we could also just put our cat on the wireless chargers, rendering them completely ineffective anyways, because our phone's not going to stay on them. So other possible attacks that we have are this one here showing, this is specific to devices with OLED screens. So I believe many modern Androids have this feature, but they can dynamically turn pixels on and off. So as more white pixels are shown on screen, the current draw also increases linearly. So we could determine like maybe a notification showed up on screen or they're getting a phone call or some other sort of info if we had more sophisticated monitoring equipment. This is also one that they performed using their $30 test setup where they were able to monitor these spikes that occurred as someone was pressing different digits of their passcode, so they could, with high certainty, infer what the length of the user's passcode was or whatever else they were typing in, because the power draw momentarily spikes when you're using your touch screen. So some future considerations is, what would the real world impact be like if we were to perform that meaningless code injection that we talked about before? Would it be noticeable to mobile phone users or not? We also, if we had access to oscilloscopes with this sort of wireless charger setup, what sophisticated attacks and what sort of information could we gather from it? Other power side channel attacks have been shown to gather things such as RSA keys and whatnot.
Yeah, so on the cryptographic algorithms, I think the group before us touched on that. So theoretically, if we were to do that with wireless, it will work too. But this paper used like cheap hardware, so this is as much as they could get. Another thing was, it was unclear whether they trained one classifier for each target device. I couldn't really find if they did that or if they trained one classifier for both devices or all the devices they use, because I think that makes a pretty big impact on the like realistic attack scenario. In the case of a public charging station, we wouldn't know like what device type we're looking at. So are we gonna have to train a classifier that's able to generalize to all the device types, which is over 200 and probably even more? Or are we gonna somehow recognize which device we're trying to attack here? So that's like a problem we're gonna have to consider. Another thing is that you don't really like use your phone much when it's wirelessly charging, because it has to lie on the table. You can't just hold it like a wired charger. In that case, at least currently, this might seem weaker than a wired charging attack. But maybe like in the near future, if people start like charging their laptops wirelessly, then yeah, that would be a pretty strong attack scenario for this paper. And as for in a realistic scenario, the classifier performance can depend on a lot of things. Again, in the paper, they only mentioned Safari or Chrome browser, but we don't know if the browser use is going to impact on the website signature. And also, they mentioned that even if a phone or a device is not chip compatible, it can attach to like a charging case, and then the phone can also be wireless charged. But with that, the charging case might change the signature again. So yeah, that's a lot of things to consider in terms of a realistic attack. And that concludes our presentation, I guess. Thank you so much.
Thank you. Any questions?
Yes, quick question on the slide where you said, you talked about like the battery level, as to how it affects, the success rate of the attack. Did you say that like if you start targeting at a higher percentage, it's more effective?
It would be more effective sooner, yeah, because it would it would sooner reach that sort of threshold where the attacks do become effective.
Okay, so like if you charge from like, let's say 80% to 100%, that attack would be more effective than 40%.
Yes.
So to add on that, it depends on which device we're looking at. It's shown actually in this paper that iPhone 11 it protects it much more. So like if iPhone 11 is at 80%, you can't really attack it. But for iPhone 8, actually, when it's like above 80% or like 90%, you can actually already start to like see fingerprints. So it actually depends on the device. Sometimes they, improve it and kind of like try to fight against this. But yeah, the main idea is that the higher the battery level, the more direct the relationship is going to be.
Okay, the picture mentioned like why specifically a higher battery level makes the attack more successful compared to a lower battery level?
Yeah, so it actually has to do with the charging cycle, because with a low battery level, what you're doing is you're supplying a constant amount of voltage, of current, sorry. So that current is going to be like in the graphs that we showed. They're going to be like monotonic. You can't really see any signature because the amount of current provided isn't affected by what you're doing on your phone.
So at first, it's just trying to provide as much as current possible, and then once it gets close to 100, it goes
So
down.
yeah, it drops.
Basically, yeah.
And then you use that gap to kind of like,
You get a lot of current fluctuations when you get closer to 100%.
Yeah, and that's
Yeah.
where these patterns start to emerge.
If you're completely fully charged, like the accuracy will be really high on that because that means your phone is only requesting current supply when you're doing something, because your phone kind of only loses battery in this case if you're doing something.
Mhm.
Otherwise, the charger is not gonna supply anything.
Yeah.
thank you guys.
Thank you.
It's a message that you are in some republic and don't charge your battery, you're charging, then use internet, or if you're using internet, just do random stuff, don't check your bank account and stuff like that. I mean, these things are, I mean, the message is not that, these are happening every day, but it's something to consider, right? So that's the whole, I mean, that's the direction, unfortunately, that we're going. Great, but I think at this moment, that's where we are. But of course, as you guys very nicely mentioned at the end, there are lots of, practical issues that make this attacks not, as dangerous as it might sound, but I mean, again, the small possibility that, someone can actually extract some useful information from your system should make you think about, okay, what can we do in order to protect our systems? All right, yeah, thank you. There's also another similar paper to this was with cars, actually. So like, Teslas and electric cars, they show that, a compromised, electric station can also extract lots of useful information about your car and then steal some information about your system and so on and so forth. So, I mean, the whole, the direction of, public stations for charging is also something that's getting more and more interest these days because technically they can extract some useful information from your system. Any final questions? Thank you, guys.
Thank you.
Yeah, it's all sharing.
Yeah, you saw.
Okay. So, so we're kind of getting to the end of the quarter. What is remaining is 1 big lecture around hardware security, which I'm going to talk about hardware security, various aspects of hardware security in next lecture. On Tuesday next week, we're gonna do our last round of paper presentations, and I'm gonna also do a quick review of the things. And if anything remains from Thursday, I'm gonna cover it on Tuesday. And our next Thursday would be our last session. I'll do the final wrap up, and then we're gonna release the quiz during that time as well, so you can actually take the quiz in the class if you want to.
In class.
Yeah. Or you can just, do it online if you want to, but
Would you
either
help
one.
us more if we do class?
What's that?
Would you help us more?
I'll be here if you want to, yeah. So I'll be technically here during your class time, so if you want to take.
Or we start with take that and do it on.
No, you same as any other quiz that you have ever taken, right? So.
Encourage people to come to the class.
I don't encourage you to do anything, though. I mean, I'll be in the class, so if you want, you can take it in the class.
So this week it's gonna be on Thursday.
What's that?
It's gonna be on Thursday.
On Thursday, yeah.
Okay.
And we still.
I mean, no, I mean, given that, we don't have anything, I mean, the class time should be sufficient for taking the quiz, so,
Okay.
yeah.
Wait, we will only have the class time or we'll have all day Thursday?
No, well, just the class time, because the quiz will be short.
Oh, so We have to take it 10 to 12
Yes,
on Thursday.
yes.
Oh,
Unless you have a conflict, which I don't think you should, but yeah,
This Thursday or next?
next Thursday. Okay. Last session of the class.
Is it,
Right.
I'm sorry, is it gonna be the same format? as,
Yeah.
Hey, so, regarding the paper review, is like next Tuesday the last set of paper reviews that we need to?
Yes,
Because like technically week 9 meeting is the one that's due next Tuesday.
yes,
And that's also what it's presenting next week.
yeah, and then you don't have anything on week 10, basically.
There's no week 10 review.
Yeah, so week 10, you have to just study for your quiz and work on your projects.
Okay, so like there's no week 10 reading method.
There is no, I mean, if you had more people in the class, they would have, but the initial plan was like having both presentation on Tuesday and Thursday, but since there's enough people already, everybody has presented, there's no need to do that, so. Yeah. So I mean, remaining work for you guys is this week paper reading, the project, and studying for the quiz. And the quiz would be everything after your second quiz. Okay? Yeah. So I'm
and do
gonna-
you know when the first project is gonna be graded?
I'll try to finish the grading this week. So hopefully we have the grades for your second quiz and the project this week. But I mean, generally, if you put, I mean, if you're, if you correctly, put your name on the blockchain and you created your own blockchain, you should get the fun full grade. It's more of like a 0-1 kind of thing. Yeah,
I use the main course for the blockchain, that's why.
you should be fine. Yeah.
When we take the quiz next week, are we coming here to write on paper?
No, it would be the same on Grayscope, so you should bring your laptop if you want to take it here. If you wanted to take it at home, you just take it at home.
Oh, we could, but we don't have to come in person.
Yeah, I mean, it would be during the class time, that's the only difference. I'll be in the class, if you want, you can come to the class and ask questions, otherwise you can just do it at home. What's that?
Is the quiz gonna be like?
It would be probably like 1 hour, 15 minutes or so, so I mean, we have a question of like, 15 minutes here and 15 minutes there.
It's not like you have to like be here exactly at 10 and it's only 10 to 11.
No, I'll probably start it at 10:30 or something.
Okay.
And then until 11:30, for example.
Okay.
Yeah. All right. Yeah, I'll post these on on Campus Wire as well. I think the one final thing is also, I think the course evaluation should be out. Is it out already or not? Not yet? Yeah. Yeah, so try to fill that in as well, because this is the first time you're teaching this course, so provide as much as feedback as possible. What do you didn't like, specifically about the paper presentation and generally paper reading? Do you think that was helpful or not? Do you think in the future offering we should do it more, less, changing the format? Another thing is I want you guys feedback from is the topics that we covered in the class. So I mean, this is very wide, area that we covered. We started from system, algorithm, then talked about, architecture and even hardware that we're gonna talk about in the next lecture. So tell us what you did like and what you didn't like, what you're interested to know more, so we can tailor it for the next offering, okay? And hopefully you guys get interested in these topics, so you can dig for yourself more as well in future. Okay, so I'm gonna let you guys go sooner today. On Thursday, attend the class if you can. We're gonna talk about interesting stuff about hardware Trojan and hardware security and all those kinds of things. Okay. Any final questions? All right.
Thank you.
Yep. See you guys later.